Hi, today we will learn a dipole which is placed in uniform magnetic field. Have you ever noticed a magnetic compass needle which is kept near a bar magnet? You will notice that compass needle is deflecting, it is rotating, and that rotation dies out in a moment. So rotation is induced by one torque, a torque which is due to uniform magnetic field. When you placed any dipole moment in magnetic field, it experiences some torque, and this torque initiates a rotation. And after some time you will see that the rotation dies out. It suggests that there is an opposing torque also acting in opposite direction and which has counterbalanced the first torque. And this torque is due to moment of inertia of the body. So let us see. Here in this very diagram you can see initially a compass needle in figure 1. In figure 1 a compass needle is placed in magnetic field of Earth, and North Pole is pointing towards North geographical pole of Earth. Here you have a hidden South Pole inside. Now when this compass needle is placed in this uniform magnetic field, then you will notice a deflection, and then the needle comes to rest. Here it is deflected. Initially it was in this direction, and it is deflected by this angle theta. Okay. So two torques are acting. Torque 1 is due to a dipole moment, due to a dipole placed in dipole with dipole moment small m is placed in uniform magnetic field B, and the torque tau 1 is equal to m cross B, as you know, and this is equal to mb sine theta. So this is your first torque. When angle is very small, this theta is nearly equal to 0. So you know that sine 0 is equal to 0. Therefore, sine theta can be written as it is nearly equal to theta only. Therefore, your torque 1 becomes equal to mb theta. Say this equation 1. Now that compass needle has some mass, and due to mass it will oppose any kind of translation. It cannot translate unless any external force is applied on it. Similarly, it has a rotational inertia also, and the rotational inertia is called moment of inertia. We can understand this in this way. Take linear analog of this rotational thing, that is Newton's second law. This is the best way to understand, because Newton's law is known to students from very beginning, from class 6-7. So Newton's second law says that force is equal to mass into acceleration. And if you take its rotational analog, so you will have to replace force with torque, because torque does the work that force is doing in translational linear dynamics. The same work is done by torque in rotational dynamics. It induces a change in velocity in rotational dynamics. So force is replaced by torque, mass is replaced by moment of inertia I, and linear acceleration is replaced by angular acceleration alpha. Here alpha is angular acceleration. Like we say that acceleration is d2x upon dt square. Your angular acceleration is equal to d2 theta upon dt square. Here theta is your angular displacement. So you have two torques, T1 and T2, and T2 is opposing the first torque, T1 torque, and so why the needle comes to a rest after few moments, and it comes to rest at one position, at one angle. So the two torques are opposing each other, and the two torques are equal at that angle. So let me equate. On equating, one and two, and they are opposite, so we need to put a minus sign also. So here you have I alpha is equal to minus mb theta. Therefore, alpha is equal to minus mb upon I into theta. Let this be equation A. Now, if you consider a case of simple harmonic motion, because when it vibrates, your compass needle vibrates, it may vibrate with simple harmonic motion. And we know in simple harmonic motion, acceleration is proportional to displacement. If you take the linear analog of it and with a minus sign, because the two directions are opposite. And its rotational analog is alpha. Alpha is proportional to minus of angular displacement. And this alpha, which is your angular acceleration, this is equal to minus omega square and theta. We know this from class 11, so I'm not going to give any emphasis on this one. Here I'll tell you that omega is angular velocity. That is equal to angle per unit time, or angular displacement time. So if you take time as one time period, in one time period a complete circle is executed by moving particle, and so it makes angle 2 pi. So value of omega is 2 pi upon t. Now when you compare A and B, you will see that in right hand side theta is same, in left hand side alpha is same. So omega square must be equal to mb upon I. Now, therefore, I, on equating A and B, we find that omega square is equal to mb upon I, or 2 pi upon t is equal to root under mb upon I. So this is the equation. And suppose you are to find magnetic field, unknown magnetic field due to some source. So this is a better way, good way to place a magnetic compass needle of known magnetic dipole moment in the vicinity of or inside that uniform magnetic field. So your and watch the oscillation of vibration of that magnetic compass needle. So you will notice time period for 5 or 10 oscillations, and then you will find time period for one oscillations. So in this way you can find magnetic field, unknown magnetic field present over there. Here I is moment of inertia, and you know that moment of inertia of a rod, simple rod, along a perpendicular axis, because the compass needle is fixed at the center, has fulcrum at the center. So along of a rod along a vertical axis is equal to ml square by 12. So everything is known in this equation. Time period can be physically noted down, seeing the vibrations of the compass needle in the magnetic field. So this can be noted down. Dipole moment of the needle is given already, and moment of inertia is equal to ml square upon 12 along a perpendicular axis from the center of compass needle. So putting value of all these things, you can find the value of the unknown uniform magnetic field. Magnetic potential energy stored in a compass needle when the compass needle is placed in uniform magnetic field. So you know potential energy is equal to work done stored in the system in any field. And work done is a scalar product of force and displacement. So if you take the rotational analog of force, it will become torque dot and ds. It is your rotational analog of displacement, that is angular displacement d theta. Therefore magnetic potential energy is equal to, for torque you can write mb sine theta, and for small rotation, if potential energy du, let the potential energy, it is du only. For small angular displacement, d theta. Okay, so du is equal to mb sine theta d theta. Now total potential energy of the system, can be obtained by integrating the equation. Therefore, on integrating the equation, you get du is equal to integration of mb sine theta d theta, and this comes equal to integration of sine theta is minus cos theta, minus mb cos theta. So this is your potential energy of the system. Now relation between balance, equilibrium and potential energy of the system. So to understand this, I have taken a cone and I have placed the cone in two conditions. Firstly, I have placed the cone with its base on the table, and secondly, I have adjusted it with little adjustment with its tip down, means upside down condition. Now you will see that in the two conditions, center of mass are at different heights, because center of mass always remain close to heavy portion. Here you can appreciate that maximum mass is towards base, so center of mass is at smaller height in case 1. Here center of mass is at only h1 height. And second case, in this case you will find that h2 height is large. So potential energy in the two cases, mgh1 and mgh2. And therefore potential energy in one case should be smaller than potential energy in second case. Now which is more balanced? So for finding that, apply force, equal force on the two. You will find that in first case, when you apply force and when you then release force, then the cone again comes to its initial position after releasing the force. But if you apply the same force, you even touch for a while, it never stops and it falls down on the surface of the table. So this is in balanced equilibrium condition, and you can say that this is in unbalanced equilibrium condition. And you can correlate the balanced equilibrium with potential energy. When potential energy is smaller, you have balanced equilibrium. If you have potential energy large, you have unbalanced equilibrium. So in this very case, potential energy minimum will be obtained by putting theta. Putting theta is equal to 90 degree. You will get minus mb cos 90 degree, and this is equal to 0. This is the minimum value of potential energy. So at 90 degree, the system will be in balanced equilibrium. Now, when you put theta is equal to 180 degree, you will find that potential energy is maximum, and this is equal to minus mb, okay. Cos 180 degree, and cos 180 degree is equal to minus 1. Therefore minus plus mb. This is your maximum potential energy. This is a case of unbalanced equilibrium. And this is the case of, for minimum potential energy, this is the case of balanced equilibrium. Of the system. of the magnetic compass needle.